The remaining parts of the software process that I'm going to talk about are coding standards, verification, and maintenance practices, and what to do if you have a publicly distributed code. What are the things that you need to be careful about? Coding standards, they are absolutely essential for code maintainability because a consistent code is much easier to maintain than an inconsistent code. What's required is that someone who did not develop a piece of code can come in and make sense out of it and maintain it if necessary. This also allows for the data structures to remain more consistent, and this is my particular I guess you can call it obsession or bias, is that I think that the documentation standards should also be included in the general coding standards so that people provide a certain minimum level of documentation that somebody not very familiar with that code can come in and make sense out of it. And you could say that we have learned the importance of all of these at Flash Center through hard experience, because what happens is it's a transient population of students and postdocs that come in. They have their own interest, they develop their codes, and as long as they're in the center, they're maintaining it. Then they move on, the piece of code is still sitting around. They sometimes continue to maintain it, but at other times people move on to do different things, and all of a sudden you have this piece of orphaned code sitting that no one thoroughly understands and no one can maintain. The good part is that because there is a wide range of expertise in the center, there's almost always someone who can make sense out of somebody's code, provided there is enough documentation for that to happen. Which is why we started insisting that people write extensive inline documentation and header documentation, both of them, so that somebody with relatively similar expertise can go into the code base, make sense out of it, and start to maintain it. The other part of it is that if you have a well-documented code, it is much easier for a user to pick up that bit of code and customize it for their own use without having to work with the Flash Center developers. So it basically makes for an easier. So the coding standards typically involve things like naming conventions and the code organization and inheritance. So well, this is the part that Sean already used that I hadn't yet talked about, coding standards. Namespace directories are capitalized and organizational directories are not. Now the biggest advantage of this is, for example, if you use a brand new directory, brand new unit in Flash, you do not have to rework the build system, because the build system is designed to search for capitalized name directories and start looking for the corresponding init data and a doer function. So you can just totally add a directory and by magic have your unit be compiled into the code if you ask for it in the configuration script. There is no need to modify the build system at all. All of the API functions of a unit start with the capitalized unit name underscore followed by the function of what that does. Subunits have composite names that include the unit name followed by a capitalized word describing the subunit, for example, grid particles, particles mapping, particles main, and so on. Notice that even though they will implement some section of the API itself will still continue to have this kind of a name. It's only the subunit directory which has this kind of composite name. Private unit functions and unit scope variables are named with 2 letters picked up from the unit name and then an underscore. And when you have a subunit, that can become a much more composite. For example, a grcreate domain is a function that resides under grid main, but then you can have a grpt init, which tells you that that is a local function that exists under grid unit and is in grid particles. What this does is, because it's a flat directory structure, and we follow similar naming convention for the data also all the way up until the kernel level, because what this does is, as long as people are diligently following the naming convention, just one glance at the name tells you whether that is a function, where did that come from, what sort of functionality does it belong to, and what is its scope. So within files, the constants are all uppercase. So that basically just tells you straight away which is a defined constant and which is not. Within routines, the variables that are of unit scope start with the unit underscore variable. For example, EOS int switched this. The name itself right away tells you that this particular variable is accessible to any function within that unit, irrespective of where that function lives. And then variables begin with lowercase additional words. These are just the details of the naming convention. And I've already alluded to the reason for significance of capitalizing name. The other coding standards, the use of implicit none and use with only. The purpose is to enforce the explicit declaration of every variable, because the Fortran has, as I mentioned earlier, Flash is written in Fortran, and Fortran allows for implicit naming, which makes for extremely hard to maintain code in terms of debugging, etc. And also, if a variable, for example, is coming in from another module, data module, it provides for an easy traceback mechanism if you have an only in there. Because if you just said use, say, grid data, and say you said use gr underscore pt data, and there were some variables defined under there, if you and you use them in some other file, you didn't necessarily know where that was defined. Whereas if you have an only, you can have a traceback mechanism whereby which is the data module that you're trying to get it from. And also this gives a protection for variable names without worrying about replications, etc., etc. We also insist on defining explicit interfaces for all of the API and the subunit API level. Again, Fortran allows you to work equally well without defining these interfaces, but they make for a much easier debugging tool, because if you enforce interfaces, then some type checking is done by most of the compilers, and they flag a compiler error as opposed to running into an obscure execution error when you're running the code. We also insist that every function, that there is a single function per file, as long if it's accessible by other functions. So only time that you have more than one function in a file is if the second function is completely locally used by that one function. So anytime a function is callable by another function outside of this one, it has to be in its own file, again for the purpose of tracing back the source readily. The documentation standards include API description and the examples of user functions. So if you go to Flash's user pages, there is the online API description, and all of those APIs tell you things like what that function does, what is its interface, the input arguments, the output arguments, the expected results in the output variables if you have the given range of values in the input, and whenever applicable there are examples for usage of those functions. These are the kinds of coding standards, and so because Flash is done with Fortran doesn't enforce most of these coding standards. As a result, what we do is we have devised scripts that run and that flag the violation of coding standards, because the code will run fine whether people stuck to the coding standards or not. But then the more you allow this to happen, the more you allow people to get away with violating coding standards, the harder it becomes ultimately to maintain the code. The next section is the verification process. As Hals already said, you obviously need to verify your codes for correctness, because there is, and this is an assertion I think anybody who's actually worked with real codes will make, there is no such thing as a bug-free code. If anyone tells you that their code has no bug, they're lying right away. Because any code is only as good as and only as verified as the tests that you've been able to devise for them, right? You can't possibly state that you've thought of every possible way in which a code can be exercised and that you've accounted for all of the different ways in which the code can be exercised. And therefore, and this is my personal experience, is that devising a good test for a code is nearly as important, sometimes more important, than devising the algorithm. This is the functional component itself that you need to verify, and everybody does that as they're developing the code. But when you're working with a multi-physics, multi-component code, then you not only just need to test for the correctness of that particular component, you also need to test for the interoperability correctness of the function of these units when they play together, right? And so you have to have tests that combine components in many different ways, and as your components increase, the ways in which they can be combined increase, the possible combinations increases non-linearly. So now theoretically what makes a good case is very easy to say. You say the test should exercise your code component in that all possible execution paths are explored, and this is impossible to achieve. Even if you have a small enough piece of code and you can devise in every possible code component processing, running such codes can be extremely expensive, so you can't really have an exhaustive path exploration. It should have a minimal dependency on the code components that are not under testing in that particular test, because again that obscures it makes it pinpointing the cause of the error in the test much harder. If you're turning it into a unit test, then ideally there should be an alternative way of computing the same solution, because just doing the same thing over and over again doesn't necessarily tell you much about the correctness. So you should have an analytical or a semi-analytical way, or a completely alternative computational way by which you can generate a solution and you can compare against the component the solution you're generating through your component. If you're running a regression test, which is where you're running the same thing over and over again, then you should have reproducible results being generated. It should not take very long to run, and it should be very easy to verify the results, because if it requires some human being coming in and visualizing and inspecting and running many different analysis tasks in order to certify the correctness of the code, then you can do it once or twice. You can do it during development, but you cannot do it as a regular maintenance practice. It's just not feasible. So in Flash, we have paid a great deal of attention to this kind of verification process, and there's a full-blown in-house test suite that runs nightly on multiple platforms, and by a platform I mean a particular combination of a compiler suite and the libraries built using that compiler suite that run every night and flag errors every night. So this is what a Flash test suite typically looks like. It lists the dates. If there is a green light, it indicates that all the test runs were successful. If it's a red light, it means that at least one test failed. And when you click upon any of these links, what it tells you is that it gives you more statistics about that particular test. So I thought I'd give you a run of. We started out with this, and then we found that this is not particularly informative, because then you always only have red lights, because every day at least one test will fail, right? So then we made different other levels of notification. So for example, the yellow light tells you that yes, some tests failed, but there isn't any test that failed in a way that they hadn't been failing before. So it's the same way that it has been failing before. And then there is this red with there is the red with an exclamation mark, which tells you that not only that some test has failed in, say, execution, but that at least one test that had been failing before has failed in a new way. Okay, so all of these notifications happen. Now let's explore. If you hover over a particular date, it gives you the list of tests that failed. And notice that many of them are saying that failed in testing as before. What that says is that if a test failed in compilation or in execution, then it's a red light, period. It's a yellow light only if every single test executed and ran and got compared and it failed in the exact same way as before. One of the first things that we did in Flash in order to make it easy to inspect the correctness of the code was to build a comparison tool. What this comparison tool does is it takes two different files, compares the output of these two different files on a block-by-block basis, and computes the error norm for these compares block by block basis, and if it turns out to be that any of these blocks have errors outside of a given tolerance level, it flags that as an error. So let's go to a day where there isn't any point in looking the test that successfully completed. So we're looking at BLAST BS, which is an MHD test. It's a one-dimensional MHD test where, well, he's done it in 3D mode, never mind, where it's the details of the test are not important, but the things that it tells you is this is the information of the way the test was run. This is the log of the test, which tells you what happened during the output, and it will inform you where and how the test failed. This gives you the setup line of the code run and the list of units that were included in running this test. This is the header file that was generated by the test, and header file is what I told you is what is generated during the configuration time that gives you things like index into the global data, into the data structure, the field variable data structure, etc. Here is an example. Your density variable is the first index, your divergence variable is the second index, and so on and so forth. So all of these files you can inspect. It's compared against two different benchmarks, actually 3 different benchmarks. One is an approved benchmark for a run starting from initial conditions, which means from time step 0. One is an approved benchmark for a run starting from a checkpoint. And the third one is a benchmark from the output saved from the previous day's runs. So the first thing that the test suite does is it compares today's output against yesterday's output. And if they match, then it tells you that the test at least is doing the same thing as it was doing yesterday. Then it compares against the approved benchmarks, and if there also it meets with success, then it tells you that the test is successful. If, on the other hand, it finds that it's not comparing well against the approved benchmarks, then it is marked as the test that is failing in the same way. And this is applicable to the regression tests. Here we saw that compared against yesterday, it was a success, but compared against the approved benchmarks, it is not a success and there is an error coming, so a failure is flagged. The other kinds of tests that it runs a whole bunch of unit tests, and in the unit tests, all that happens is there is the only output coming out of unit tests is typically whether the test failed or passed. So there are built-in mechanisms for verification of answers. That's what the flash test does, and it runs on, as you saw, on 4 or 5 different platforms, and the reason for that is different compilers catch different kinds of errors. And this is completely necessary to be able to trace day-to-day errors introduced during the course of development of the code. But the test suite by itself is not the whole story of the verification process, because, as I said, the tests you devise are equally important. And then there is this business of how many tests should you include and what should be the criterion for including those tests. How should you orchestrate your test suite, because you can't do exhaustive testing. It just would take too long. In fact, we had gotten to a point where we were using people's workstations over the night to run the test. People would come in and the test would still be running, and people wouldn't be able to use their workstations because the test suite was hogging all of the resources. So you have to very carefully select the tests, and you have to do this while still making sure that you're providing as much coverage as is possible. So we do this we check for coverage using this matrix, and this is a very small example of the kind of matrix we generate. So what we have done in this example is we have 3 physics. So we have infrastructure along the columns, the physics along the rows, and what we do is then we start to list tests. So the first test is a simple unit test for particles, and when we fill in particles for that. With the test number 1, particles unit is covered. The second test is a unit test for gravity, self-gravity, and this particular test also uses by default AMR. So the second test is providing a coverage of self-gravity under AMR. And the third test now is a genes problem, which is making use of unsplit hydro, a parallel IO along with AMR. So this will fill up the appropriate columns that it's testing for. Genes problem also uses self-gravity, so it's testing for self-gravity under AMR, it's testing for HTF5 IO and uniform and unsplit hydro and HTF5 IO with self-gravity. So this is how, and there are the test numbers 4 and 5 that do the similar. So now what happens is we know that we still have spots here that are not covered, and we need to look for more tests that we need to cover these spots. And so we keep looking for tests until this matrix is full, and that's how we basically produce the list of tests that we are going to be running on a regular basis. The methodology for picking the selection of tests. The unit tests are almost always the cheapest, and of course they need to happen because that's the only way of checking an individual component thoroughly itself. So we pick all the unit tests first. The next set of tests that we pick up are the setups that are covering the ongoing research within the center, and we fill the matrix with the corresponding coverage provided to the code. Then we start to pick tests that are, for example, known to be sensitive to perturbations, because those are the ones that are following the more unusual execution paths within the code. So next we pick those codes. Then we pick the tests that are known to exercise solvers in unusual ways. And finally, whatever empty stops are left, we pick the least complex setup that would cover those. And the reason is because the less complex a setup that you use, the easier it is to narrow down on the error that occurs. So if you can find the same error by running a less complicated application, the task of resolving the test becomes much easier. So this is the whole verification process for Flash, is that it uses the unit test is done by the test suite and software. Comparison tests are done by the test suite. Then what happens is this also doesn't cover the entire verification process, because then you have a new platform that comes in, and all of a sudden you have to port the code. So now again a human expert has to come in for manual verification. It happens sometimes that you make a change in the code significant enough that all of the currently approved benchmarks become obsolete, because maybe you introduced a solver where the tolerance increased, or a new version of the compiler came in, or some such thing. So again, you have to have a human expert intervene. And then if you introduce a new test platform, you have to have a human expert and a suite software. All right. And I will try to rush through the remaining slides. I don't have a whole lot more left. But the maintenance practices is that you have to have rules for repository management, which means that you have to decide whether you want to have a proper gatekeeping process involved, a gatekeeper there, or you just want to depend upon the individual developers to be responsible enough. How far do you allow branches to diverge? And that varies from project to project. There are projects where they say that you can take off a branch and you do whatever you want with it. But if you want to keep a common infrastructure supporting a large variety of capabilities, you cannot let the branches to diverge very much, because the reconciliation becomes nightmarish. How much of access control do you apply? And then there is the question of verification management. So it's all very well to run the test suite, but if no one's monitoring on a regular basis and doing something about it, then it doesn't help any. So for example, in Flash, the policy is that if you have a test in the game and your test failed today, then either you have to signal the fact that you know why this has failed and you're going to be able to resolve it, and it is not affecting the other tests, or else you have to solve it, you have to prioritize fixing the breakage that happened. Similarly, coding standard management is how much do you insist, because these are all thankless tasks in some sense, but they are necessary tasks also So what do you do that the new code is sticking to the coding standards, and in terms of documentation, what fraction of the developer time is reasonable? So in Flash, for example, we don't have a designated gatekeeper except the local core Flash developers and somebody getting annoyed when things are broken. The collaborative development branch is the only one where outsiders have access. Everything else is locally owned by Flash, and it has also become the primary development branch. Different branches exist for specific projects. The code group manages the weekly merge schedule, and the concerned developers are expected to make sure that the issues flagged at the merges are resolved before the next project is scheduled to merge, because this whole process will break down if we didn't stick to this. Now this repository management is where we actually get very, very complicated, because we have multiple projects that run. So every development branch, there is a production, if there is a production schedule, there is a corresponding production branch. And every project that's running off of that production branch is then expected to have its own project branches. So the stable revisions of development branch are tagged and merged to the production branch. This is to make sure that when a simulation campaign is going on, in the middle of the campaign, things don't change and break. However, no simulation campaign should run directly off of the production branch. It should have its own project branch into which even these merges that come into the production branch do not get forwarded. And no forwarded merges occur on the campaign branches. Backward merges are rare, but they do happen, but they have to be done manually and with carefully monitoring the impact on them. All of this only works if all the participants that are making use of these repositories buy into the practice. And for the verification management, all the developers are expected to provide tests for new capabilities that they add to the code. The tests do get added to the test suite. The developers are expected to monitor the test suite, and usually someone takes the responsibility of day-to-day management of the health of the test suite and basically bugging others if things are consistently failing in test suite and making sure that they take the time off. The thing is that the test suite is taken very seriously at Flash, and everybody who has been at Flash and gone on to work elsewhere takes a version of test suite with them and starts to get going with them, because they have learned the value of it and they will not live without it anymore. Coding standard management, we have set of scripts that run on a nightly basis, and they flag violation in the coding and documentation standards. It's not that these things are corrected every day, because that would not be cost effective. What it does is, usually new developers tend to see where they're making too many mistakes in sticking to the coding standards. And this is where our regular releases come into play, in that every time there is a code release, the coding standards are, so the coding violations are inspected and updated, so that at every release the code is up to the standard, up to the total coding standard. And I think I'll skip over the documentation. The important things to remember are that if the code is public, then the documentation, just inline documentation and header documentation is not enough. You need to have users guides, you need to have online resources, you need to have frequently asked questions. If also the code accepts contributions from external users, you have to publish coding standards. You have to have coding examples that people can work with, and you have to have a developer's guide. And I'll skip over the Flash example. Anyone who's more interested in it can come to me and I'll show them to you on a one-on-one basis. If you have a publicly distributed code, you also have to do distribution policies. Let's see, here we go. In the distribution policies, you have to worry about things like licensing agreement, whether you want a purely public license, you want a restrictive license, etc. How do you control distribution, whether you're doing distributing as a tarball, whether you allow your users to distribute the modified version of the code or not, and whether you're giving it to them in a version, what's included in the release, how often do you release, and then the contribution policies. And this is where things have to be done very, very carefully, contribution and attribution policies, because many a times external users want to give you the code and they want you to maintain the code, but they're concerned about their competitive advantage if they make the code available to you. So in Flash, for example, we have a policy of a pre-negotiated time where the code contributed is maintained by the Flash developers, but at the end of that time, whether the contributor likes it or not, the code goes public. When people contribute code, we need certain things from them. For example, we need a test that can be included in the test suite. We need the documentation that can go into the user's guide, and we need them to meet with the coding standards of both the code and the documentation. And the last slide that I have is the attribution policies. So every code bit that is contributed by the external users, for example, is explicitly acknowledged in the release notes as well as in the user's guide. And also the Flash maintains a publication page where people can upload their publications, and the user's guide will point you to that publication page where people's work can get recognized, and it's all referenced in the user's guide. And I know I skipped very rapidly over the last few slides. I'll be happy to talk to people about them offline if